Good afternoon, everyone. Welcome to the 90th Prof.R.Ananthakrishnan Colloquium. Today we have a very interesting talk. We have a very dynamic visitor with us, Professor Umesh Ramakant Kadhane from IIST Thiruvananthapuram. So I would like to introduce him to you. Professor Umesh holds a PhD in ion molecule collisions from TIFR Mumbai and has international research experience in ion storage devices and molecular mass spectrometry at the University of Aarhus, Denmark, and University of Paris in France. He began his academic career at IIT Madras in 2008 and later joined the Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram, where he has played a key role in developing advanced mass and electron spectrometry systems. Over the past 15 years, he has supervised numerous undergraduate and postgraduate students, including 8 PhD scholars, and established major research laboratories at IIST, which has been focusing on fundamental atomic physics and space-oriented research and development. Professor Umesh has made significant contributions to plasma propulsion diagnostics and system development for ISRO's space programs. He currently serves as the Associate Dean at IIST, Deputy Project Director for the High Thrust EPS project at LPSC ISRO, and he is the Principal Investigator for multiple space missions, including payloads for Earth orbit and upcoming Mars and Venus missions. He has already led 2 highly successful missions for IIST, which is Ares in lower Earth orbit and gearing up for the 3rd one. He has already set up 3 major research laboratories at IIST, one for fundamental atomic and molecular physics research and 2 for space-oriented research and development. The latter to include Electric Propulsion Diagnostics Laboratory, that is EPDL, and Sensors and Payload Development Laboratory for SS Space, FPDLS. He is an avid educator with a keen interest in disseminating scientific theories and ideas among a wider reach of the student community and public. And also he's a trained mountaineer as well. So with this intro, I now welcome Professor Kadhane to deliver this announcement. Hello. 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 Hello.
Start without mic.
Yeah.
Or you can come.
Maybe loud
Okay.
enough.
You can come in front.
By the time he is working.
Come ahead.
Hello.
नहीं बंद हो गया
अच्छा सिग्नल डिपेंड कर रहा है
Let's stay.
नहीं रहा स्पीकर
Hello.
Slide. So good morning and thank you very much for such a great opportunity. This is my second visit to IITM and thanks to Dr. Bhupendra, I got a chance to interact with all of you. My last visit was in March last year and it was a very short visit, very specific work we had here. So I couldn't come to this part. I came to the guest house and directly we went to Mahabaleshwar. So it's really impressive to see the facilities and the kind of activity people are doing. And actually, when many of our students, PhD students, they are from NARL, and PhD students, we have joined, we have an MOU, so they jointly work with us. And we often have this discussion because the students sometimes get demoralized that what is our future, what I am going to get, and so on. And I always tell them that in any society or in any country, when truly science and technology comes together, then the trades or the research dimensions like atmospheric sciences, weather studies, these are areas, remote sensing, these are the areas where really the money goes. Because imagine if your inputs go into industry for taking policy decisions, you become very important. Unfortunately, in our country, we still are far away from that state, but we are going in that direction. And I think an institute like this has a very important role in validating the capacity of Indian scientists to influence the government policies. So I think in coming years, things are going to be very interesting for this field. And perhaps that is one of the reasons why we are not from this field, but we are trying to get into this field. So I'll be talking about basically my personal research interest, which is quite different than what you do, but I'm trying to sort of stitch it together as I'm trying to intrude into your area. So I come from IIST. Yes, yeah. Actually,
कोई नहीं है क्या और?
काम नहीं, maybe
हाँ,
keyboard से you can just.
What happened today?
so I come from Indian Institute of Space Science and Technology, IIST. It is situated in the southern tip of India. So we are not very popular in terms of location. Kaif is here, and we have one more student here from IIST. Basically, okay, good. So we basically work with three labs: atomic and molecular physics lab, which is the parent lab, and electric propulsion and sensors and payload development lab, which are basically sort of a outcome of the atomic and molecular physics lab. And this particular logo I will explain maybe by the end. So this is a complete span of our atomic and molecular physics lab activity. It's enormous. We work in mainly fundamental atomic and molecular physics, where we try to study how high energy radiation processes large organic molecules. That is our fundamental interest. And we build our instrumentation, mass spectrometers, and so on ourselves as much as possible. I'll show you some of the developments. In that also, there are several subdomains. So some of the facilities we don't have in IIST, so we go out and use them. We are very strong partners with ISRO for electric propulsion research. So the futuristic plasma engines, the space propulsion will be based on plasma. They are very efficient engines. Already ISRO has been successfully developing a few generations of such engines, and these kind of engines require a lot of diagnostics because of the complex physics involved. So we partner with them to do a diagnostics related activity, and we also do simulations for them. And while we do on ground diagnostics, now that India is getting ready with a new satellite which will have Indian plasma engines installed on a communication satellite, they need plasma diagnostics on board as well. So we are building that payload also, that actually should be flown very soon. So this is that will be our third mission. We are also involved in sensors and payload development activities. So we already have had 2 ARIS missions around the Earth. We are developing an orbit trap mass spectrometer for futuristic missions, 2 interplanetary missions. RPAV is our Venus mission payload, which is getting ready, which will be launched as part of India's first Venus orbiter. And then the next Mars orbiter also, we are attempting a similar payload. We have nice spin-offs coming out. We are collaborating with interdisciplinary areas and in some cases with industry to develop mass spectrometry for medical application. We are working on a landslide detection technology, in-house development, soil moisture, the project for which I am here today, and aerosol mass spectrometer development activity. I'll just quickly go through some pictures to impress you. We have the electric propulsion diagnostics laboratory, and what you see over here is our high vacuum testing facility, which basically mimics at a small scale. This is actually small. The actual plasma engines are tested in much larger facility. That is this size. This is a vacuum chamber for that. So this is at IIST. So our students basically build the electronics and the sensors. These are all sensors built by our students. And then they are tested here. They are supplied to ISRO facility, where again, installation testing is done by our students, and now we are handing over this technology completely to ISRO so that they can run this and we can commercialize this technology. Then we also had a couple of very successful space missions. So this was our mission logo for the first mission. It was in 2019, April. We launched this retarding potential analyzer pair for ionospheric studies, Earth's ionospheric studies. So the color of this logo has a blue dot, meaning it is around Earth. And when we have it around Venus, it will have a different color. Mars, it will have a different color. Hopefully, in a few years, we will have all colors. So let us see. So as I said, we have a series of space missions lined up. This was our original team in 2019. And then later on in 2023, we had another launch. This was our 2023 launch, where we again studied the ionosphere using our payload. This was the team in 2023. If you want more details of this mission, because we got fantastic data, we could actually study how the solar wind is actually interacting with our atmosphere in extreme conditions, where you have a very extreme coronal mass ejection events, how they interact with our atmosphere. We could actually see very nice signatures in these two missions. I'll quickly talk about the building capability. So here I'm going to show you a lot of machinery, but it's basically to impress upon you that we do not do the science ourselves. We need help from people like you, but we can do the instrumentation required for that. So basically, this is our payload. So I'm just giving this as an example. So these sensors are built using very special type of grids, which sit in the top section. This is the sensor module. This is the electronics module, which hosts the entire electronic board, as well as the DC-DC converters. And this is the size of this payload. And this is how it looks from inside. Of course, we can't actually fabricate these boards because these have to be fabricated by certain quality standards. But the design is ours. Then we outsource it to certified manufacturers who can actually manufacture these things. The mechanical fabrication, this one was not manufactured at IIST, the mechanical body, but now we have the capability to do it in-house, this size. Then, of course, you don't launch something just like that by making it. We test it. And since it's an ionospheric payload, it has to be tested with plasma. And in our country, there are only few such facilities. And in fact, a lower Earth orbit ionospheric facility is only one. That is one in IIST, which we have built. And again, the entire design is made by our students. So this is the facility where we subject our payload to a plasma condition. So you can't see the plasma now because the densities are close to the ionospheric densities, but we can actually make the plasma so bright that you can actually see the plasma glow in the chamber. So this is right now filled with plasma when we are testing our payload. Of course, it goes through several thermal cycles and vibration cycles before it is launched. And then we do the electrical characterization of the payload. And this is the actual data we got in the orbit, on orbit number 4, which is a 90-minute orbit around Earth, 500 kilometers, low inclination orbit. And every second we get a scan of data. If you are interested, we can discuss this more. But this blue patch is basically several thousand scans which we get over 90 minutes. And then from that, we can basically scan the ionospheric condition around the Earth. This is the event which we detected. We detected a few more events like this. There were extreme events where the plasma temperatures went beyond 10,000 Kelvin, which is completely unexpected. And then when we looked back at the history of that event, we discovered that just a few days prior to that, there was a coronal mass ejection event, and that caused a geomagnetic storm, and it was detected. Our orbit was a 9 degrees inclination orbit, so it was very close to equator. And you can imagine, normally such disturbances are seen only in the poles or close to poles or higher latitudes, but we now can see it near the equator. It was an extreme event.
This kind of temperature variations are expected, really?
No, they are not expected. So this is a kind of plasma wave, which basically came from the poles, and it was oscillating, as you can see. One single orbit around the Earth, we are seeing multiple oscillations. So this was completely unexpected. This needs to be modeled, actually. So this is basically the plasma temperatures and parameters which we measured. Our specialty is not to buy ready-made equipments. Our specialty is look into what possibly can be built. Of course, we don't build everything, but whatever we can build. So these are some of the examples to test our payloads. Just to test our payloads, we require plasma sources, ion sources, electron guns. We build them ourselves. So these are some of the pictures of these devices which we have built. Again, if you are interested, we can discuss. So these are the two facilities. This is a small chamber, about this size, 0.5 meter diameter chamber. And this is a larger chamber in our lab where we test these things. So now I come to the main topic. What I wanted to talk to you about is this. So basically, we are interested as our science research. So far, what I was telling is about instrumentation research. And just a disclaimer, one person cannot do all this. I am fortunate to sit in an institute where we have people in aerospace engineering department who are experts in manufacturing material processing. And we have avionics department where we have people from electronics, digital, analog. And so we can use their expertise. So we have actually a team of 7 faculty members, including myself, who basically work in different aspects of this payload making or instrumentation making. But now coming to this is where my science interest comes, where we try to understand how life originated. And the old theory was that we had a very nice fertile environment here with all sorts of interesting but small molecules like what we have in the atmosphere: oxygen, nitrogen, carbon dioxide, ammonia, and things like that. And then there would be lightning once in a while. That lightning would produce larger molecules. They would get deposited into active chemical environment like an ocean. And then slowly life came out of it. Well, this was proven in 1930s, I think, sometime, by a very famous experiment called Miller-Urey experiment, where they actually created this kind of situation in a vacuum chamber. No problem. That is very much possible. But I'm sure most of you are aware that what atmosphere we have today is not what it was in the beginning. 4.3 billion years back, the atmosphere was mostly carbon dioxide and much higher density than today, almost 60, 70 bar. There was a time. And if you now simulate the effects of a meteorite falling, today when in the night you see a falling star, what basically you're seeing is a meteorite which is burning. And before any residue of it reaches Earth, most of it actually is completely obliterated. It completely burns. It's into plasma. But when the atmosphere is 60 bar and carbon dioxide, things don't burn. They slow down. Okay. And when they slow down, they land with a lot of chemicals on Earth. Okay. Very close to this place, not that close, of course, is Lonar, where it's a very beautiful lake, and it has a history that there was a nice impact crater there. So a lot of material actually was entering in our atmosphere. Okay. And then the question comes, is it not possible that at least the original molecules of life came from there? But for that, we need to have evidences that such molecules exist in space, because such molecules normally wouldn't survive high energy radiation coming from a star. So it so happens that before the planets were formed, these molecules were forming. But these molecules are so delicate that up to 9 astronomical units, they wouldn't survive in a solar system which is under formation. So if you see all the planets beyond that, like Saturn, Jupiter, Neptune, Pluto, and their moons, they are filled with organic matter, something which we didn't expect. But inside, when it comes, there are only 2 places where we have proven organic matter present on a planet or a dwarf planet. One is Earth, another is Ceres. Okay. And we know that this material should not have survived. So then we can say on Earth, this material was produced on Earth. Fine. But what about Ceres? Ceres doesn't have atmosphere. It doesn't have lightning. It doesn't have cloud. It's a mini planet. It's just 1,000 kilometers diameter. So how did it acquire this material? 40% of its surface is covered with organic material. So this material was actually deposited onto these planets by asteroids and comets. Okay. So now this is a sort of an idea which is getting accepted, that at least the basic molecules of life came from outside the Earth. And then, of course, the chemistry on Earth made larger complex molecules. If that is the case, do we have evidences of that? There are several evidences. This is a list of places where there are proven organic inventory in our solar system outside the Earth. Okay. And places like Ceres, Pluto, Titan, for example, the total amount of organic matter is more than what is there on Earth. So these places are rich with large molecules. So our quest is to understand how these large molecules are produced and what is the role of the upper atmosphere in producing them. There is a reason why I say upper atmosphere. So this is one example which I will be talking about today. This is an actual picture taken by Cassini-Huygens mission in early 2000. And this is picture of Titan. Titan is one of the moons of Saturn. And interestingly, it has atmosphere, 1.5 bar, low temperature. And that atmosphere is 96% is nitrogen, about 3 to 4% is methane. Rest of it is hydrogen cyanide and other poisonous gases. Okay. And the atmospheric structure this is Earth's atmospheric structure, approximate, and this is the atmospheric structure of Titan. So what is interesting is that there are sort of this photochemical smog which is present in few hundred kilometers height here. And then here there are aerosols. Okay. So this is how the picture looks today. The radiation from the star and the energetic particles guided by Saturn, they cause a lot of interesting reactions in the upper atmosphere. Then they precipitate, forming larger molecules. Then they form aerosols, and then these aerosols get deposited on ground of Titan. And this is not just a model. Actually, a lander and took pictures, took mass spectra, took spectroscopic data, photos, this FTIR type spectroscopic data. I will show you some of that data later. And these molecules exist. These are aerosols, actually. And these aerosols are made from a material called toluene. And this material, toluene, is nothing but just like a plastic. It's a polymer of carbon, nitrogen, and hydrogen. So if you have a framework of carbon, nitrogen, and hydrogen, then there are several possible molecules which can be formed, which could later on lead to life. For example, one of the nucleobases, adenine, is basically 5 hydrogen cyanide molecules merged together. We are trying to do such experiments to show this. Okay. So in the upper atmosphere of Titan, this is the molecular composition. You can see this is from 1000 kilometers to 1700 kilometers, and different complex molecules are present. The other problem, which is a real problem to understand today, is that what happens when you have a planet and you have an atmosphere, the solar influx causes some disturbance in the upper atmosphere, and then that influx which causes that effect, then it will diffuse laterally. So when there is daytime, you have one sort of molecular structure, and nighttime you have another molecular structure. The nighttime molecular structure should be decided by whatever can survive from the daytime and whatever can diffuse from the daytime. So there are models which try to understand that, and we apply them for Earth very successfully. But none of those models work when it comes to Titan. So for some strange reason, Titan shows some very strange behavior in terms of how this radiation effects actually propagate. Okay. Now, when it comes to atmospheric models, most atmospheric models consider only photo-induced reactions, especially Earth's models. We normally ignore charged particles or so-called cosmic rays. But they are not always cosmic rays. Even sun produces huge amount of charged particle radiation that we know. That is the one which gets trapped and we get the aurora phenomena in our atmosphere. But these fellows also come with large amount of energy. And this energy also can cause a lot of interesting effects. Normally they are ignored. Okay. So this is one example. Again, this is Titan. This is actual measurement. And what you see over here is a flux of hydrogen, 20 to 50 keV hydrogen. Okay, this is a distribution of 20 to 50 keV hydrogen, and you can see this is hydrogen, not proton. Okay, question is, where does it come from? I will skip this part. This proton actually comes from sun, and then as these protons approach Saturn, because Titan doesn't have magnetic field, but Saturn has magnetic fields, very strong magnetic. So this magnetic field of Saturn guides these protons onto Titan, and the Titan atmosphere basically neutralizes them, and you get this neutral hydrogen. And now this neutral hydrogen can actually penetrate inside the atmosphere and deposit all this energy inside the atmosphere. And this is a comparison. This is the photon flux at 1 astronomical unit, that is where Earth is. And this is the charged particle flux, proton flux at Saturn. And if you scale this to 100 times, because they are 9 astronomical units away from sun, then you will see that the flux actually matches. So the solar flux in terms of high energy extreme UV photon is numbers matches with proton, but protons carry much more energy. Okay? And very high in interaction cross section. So they interact very rapidly. So we are trying to understand what are these phenomena which people have so far ignored. Can they explain the strange behaviors which we see? And finally, can it also sometime explain how the molecular life originated in space? Okay, so for that, we need to go to molecular physics. So this is what we basically do. We take various types of radiation processes. We take molecules which would be very close to organic molecules, and we subject them to such kind of radiation and try to understand the effects. Okay, again, we are searching for universality, because there are thousands and thousands of such molecules. If I keep studying each one of them, it's meaningless. So we are looking for universality so that we can build models which can then directly be applied to how the atmosphere of a planet would evolve and produce molecules of life. Okay, so we use several techniques. I wouldn't really list all of them here, but we basically take radiation, energetic radiation processing. We look at statistical processes of excited molecules, and we also try to do laboratory simulation of ionospheric conditions. So as I said, we use facilities in-house and outside IIST. So these are some of the facilities we have been using. One in Italy here. This is a synchrotron radiation source as a source of extreme UV radiation. This is a proton beam facility in New Delhi, which is again mimicking the solar flux. Both of them are used to sort of model the solar flux. We also use two other very interesting facilities to prove our point. These are the instruments which we are building at IIST or built at IIST. They look messy because they are sort of home built. So we have something called energy correlated time of flight mass spectrometer. It's a very unique machine. It is the only machine today in the world where you can actually study a molecular dissociation process from nanosecond time scale to millisecond time scale in a single shot. We have developed this technology in-house. Okay, I think I will skip this part. I'll just show you how the machine works. We have a nanosecond pulse laser where we cause ionization, and it's a nanosecond pulse laser. So the formation of ions is within nanoseconds, and then we accelerate them towards a detector. It's a standard time of flight mass spectrometer. Your labs also, some of your labs have this kind of instrument for studying aerosols. But instead of just taking a time of flight mass spectra and just identifying what masses are there, we add one additional spectrometer in between with a position sensitive detector, and we try to track the trajectory in real time. And that gives us the ability to sense the dynamics of the molecule. So in the other research labs, we have instruments which target this dynamics. This is dynamics which happens over milliseconds to seconds, or there are instruments which track dynamics from microseconds to nanoseconds. This in-between part was completely missing. This is where our instrument fills the gap. So coming back to Titan, what we want to try and understand is basically how all this yellow material was produced and what is the possibility that such a material can ever give rise to or host a molecular life. In fact, there is a strong possibility that even a microbial life can actually form in these places. And by the way, the entire thing, what you see, this yellow, brown haze, these are all aerosol particles. And those particles have precipitated on the ground as dust. And these are all polymers containing carbon, nitrogen, hydrogen. These are the measured mass spectra over there. And if you zoom into the mass spectra, you can prove that they are made out of carbon, nitrogen, hydrogen, because you can see these peaks are the mass spectra and they are separated by masses 12, 13, and 14. So you know that these can come only when you have combinations. Okay. So we are trying to understand how the solar wind, as it interacts with the Saturn's magnetosphere. This is Saturn and this is Titan, and this is the plasma sheet of the surrounding environment because of the magnetosphere of Saturn, and how this radiation is getting concentrated onto Titan. And then we list down various types of radiation processes induced by photons, induced by high energy electrons, induced by high energy protons and high energy hydrogen, and then how they modify the atmosphere there. I'm going a little fast because I do not know how many of you really connect with that kind of detail, but I can share more details if you are interested. But coming back more towards ionospheric conditions, one way is what we were doing. You take any individual molecule, break it with a specific radiation and see what happens to the molecule. It's a time-consuming process, very close to fundamental physics, more than atmospheric sciences. But if you really want to accelerate this understanding, we also have to go the reverse way, how nature does it. So we try to recreate the ionosphere conditions in the lab. So this is one of the 3 Titan reactors in the world. We have built one prototype, and this is a Titan reactor which creates situations similar to what is there in the upper atmosphere of Titan. We take the same composition of nitrogen and methane. We put it into a vacuum tube. This is that vacuum tube here, and then we couple it with a high power RF to create the plasma condition. On Titan, there is no RF. In Titan, there is a high energy radiation coming from sun, directly or indirectly. So we create that in the lab using high power RF. And this pink glow is for argon. Then once this glow is there, we slowly substitute it by combination of methane and nitrogen. And we study this. So this work was entirely done by one master student, Veena. She built this whole thing herself. We borrowed the RF supply from somebody. We borrowed the matching network from somebody. The rest we constructed ourselves. Behind this, you see another chamber there. We take a small sample out of this and send into a high vacuum chamber here where there is a mass spectrometer sitting. It's a commercial mass spectrometer. So where we try to characterize the kind of molecules which are getting produced dynamically, and we try to basically mimic this process at least up to the top level. Okay. So again, if you are interested how we create these conditions, we can discuss this more, but I have already told you, we create the plasma using RF. So it is a high density plasma, it's cold plasma, and there are no metallic electrodes inside. So it's very close to natural condition, and we create this. So do we get anything interesting? Remember, we only injected this in the system. 96% nitrogen and 4% methane. That's all we injected. These are very small molecules. Okay. And we get, this is a glass slide, which is not subjected to this plasma. And this is a glass slide, which is subjected to the plasma. You can see there is some brownish yellow deposition. Okay. We characterize this deposition and we compare that spectroscopic signature of that with the one which was measured on Titan. And you can see that they closely match. Okay. This is done using FTIR, and the individual bonds and their intensities, they match in the two cases. And we can get this material. We also extract some molecules out of this and take a mass spectra. Remember, we launched into the plasma only nitrogen and methane. So nitrogen should be 28 mass units somewhere here, and methane should be 16 mass units somewhere here. But you can see that our mass spectra is filled with many, many heavier masses. Plasma is actually processing and producing larger molecules. So basically now we want to understand what are these molecules. Is any one of them close to molecule which can produce amino acids, nucleobases? Okay. And remember, if this can happen in a vacuum chamber in the same plasma condition, then it is happening on Titan. It is not only happening on Titan, it also happens in the tail of a comet. Okay. And this freshly cooked material is then deposited when the comet passes close by to Earth. Very rarely, but they do. And then, because the tail of a comet extends several million kilometers, and this dust slowly reaches Earth's atmosphere. Okay. And another very interesting thing about our atmosphere even today is that today's atmosphere, if a meteorite is large, it will burn. But if the meteorite becomes a micrometeorite, meaning if it is a particle which is less than 800 micron, it doesn't burn. It simply lands. Okay. And in fact, if any one of you are interested in a new kind of hobby, I can tell you that on a pristine land, every year, every square meter, one micrometeorite lands softly. If you know what to look for, you can actually find them. So my children, we have few microscopes at home. My children have this hobby. So we collect dust from as many places which we know are pristine and no industrial disturbances happened. We collect, we sift the sand, soil, everything, and we actually pick out, using microscope, we actually pick out these micrometeorites. It's a very interesting hobby, and you will find very interesting things.
So what will be the implication of such, very minute particle on those pristine lands in time?
In time, they get integrated into the ecosystem. Okay. But there are places where they don't. For example, in Antarctica, there is a full project which is running for several years now. Their job is every day truckload of ice they bring, push it into a shade, In that shade, there is a big container in which they melt the ice, filter it, and what they get is all micrometeorites. And then these micrometeorites are then studied for their composition and categorization and distribution. So it's a very interesting thing. Okay. Yeah. But anyway, so we do have such interests that such material could be processed. You see, a simple plasma device built in a lab can produce such molecules, then there is a great scope. And by the way, we are limited here because the sensitivity and range of our mass spectrometer is that much. Because our instrument is a commercial one, it has a limitation. But mass spectrometer we build, they usually have much larger range. But I didn't want to take a risk with plasma and home built instrument. So we put it on a commercial instrument. So this is the topology of the material which was produced. And then we tried to see that this picture, which I was again and again showing you, this picture, okay. So just look at this picture. You start with small molecules, radiation processing large molecules, then they condense and form aerosols and larger particles. So this is what we observe. A simple 0.1 millibar plasma produces these kind of particles. So this basically we are evolving this way. Only problem is you can't quantitatively follow the development. It's simply something which is happening. It's like cooking, right? A lot of ingredients are gone in and a lot of things are happening simultaneously. You can't do one by one analysis. So we are trying to bridge the gap between microscopic understanding of one molecule interacting with one proton and doing something, and a larger understanding of what happens in an atmospheric condition. So this bridging the two, I know many of you are also facing the same challenge. We also face, but in a different way. So finally, I'll just spend a few minutes, just 5 minutes maybe. So of course, this kind of investigation cannot be done by one lab. So 2023, we started a new initiative. It is called Organics in Space. Organics in Space is a very wide and multidisciplinary initiative. The origin and evolution of molecular life in our solar system, whether it is Earth or outside Earth, preferably outside Earth, because on Earth, it's too much of chemistry. We don't understand it. Outside Earth, it's mostly radiation processing, which we claim to understand a little bit more. So we are trying to focus more towards that. So what you see over here is a conglomeration of space technology, science and instrumentation expertise, astrochemistry, molecular astrophysics, and whatever is the complementary. So you see something in the space, you try to do something in the lab, mimicking that, what I just showed you. So we want people to work in all these domains, and we want people who are already working in similar domains or connected domains to come to us, work with us, and form a network. So this is our network. This is an Organics in Space network. All the pink dots, stars are all individual institutions from which people have joined this initiative. Right now, the initiative is purely informal. It's only a friendship network. But now, in coming months, we already had discussions with various funding agencies. And the first week of March, we have a big meeting with ANRF officials and so on. We'll be presenting our case as a consortium funding opportunity. And we have people from very different background. We have people who work in biology, biochemistry, astrochemistry, physics, molecular physics, people working in space technology, instrumentation, launch vehicle design. ISRO people also are there, so that we can actually build a robust functioning network of researchers. So we started this in February 2020 at IIST. Then we conducted one exclusive conference. So this was part of another conference where we announced this and we had a half-a-day session. But then following that, on first symposium, we conducted exclusively on organics in space in January 2024 in IIST. The second one happened last year, July, in Geetham University, Bangalore. And this is our website. And we would definitely love to have your expertise also part of this. At present, we are collected a certain set of joint proposals, research proposals, and we are going to now collect one more round of these proposals, and all these proposals are given as a single consortium proposal to ANRF as well as DOS, and also some private funding agencies, so that we can pool in the money, and then people will work in their own labs, their own places. Only their research will be oriented, or they will be supported and funded to orient part of their research towards this goal. So this is our idea. These are my collaborators. We do wide variety of activities. Some of the activities I didn't even talk about. So of course it cannot be done by one person. So there are so many people involved in all these activities from all over the world. Then students, without them, we can't do anything. So the names which are in black, they are the people who are right now working with us. These three are my PhD students at present. I have some other PhD students, but they are actually ISRO students and ISRO scientists who are doing their PhD, so they don't directly contribute to this area. Then we have staff. The names in blue are the ones who have in recent months have left us for higher studies or jobs and positions. The others are still working with us, and I think some name is missing here. I have to update this list. And these are the people who we trained in the past. This is not a full list. Not all names are there who are trained in our labs, and now they are exploring various possibilities. And of course, this is the logo of our Organics in Space. Please visit our website, have some more detailed information about this initiative, and please join it if you think you would like to explore outside Earth how life originated. We are trying to do that, and I'm really happy to be in IIST because you're always surrounded with young people, so they make you forget your age sometimes. So thank you very much for this opportunity. As it says down there, सितारों के आगे जहां और भी है, अभी इश्क के इम्तिहान और भी है. Thank you. Thank you.
Thank you, Professor Kadhane, for such an interesting talk and summing up what are the different kind of space programs and observations they are trying to take. So now the floor is open for questions. Yeah? Something?
You've seen it firsthand.
Yes, yes.
My chemistry knowledge is very limited, but
Can you
is there a
stand up?
possibility?
Yeah.
Is there any possibility for life to exist that is not based on carbon?
Okay. So there are very interesting questions which exist, which appear to have an open-ended answer. Okay. This is one of such questions. Can life exist which may not be based on carbon? Unfortunately, the present chemistry gives very limited hope and scope for that possibility. For the simple reason that life, if it has to be defined the way we define our life, that is mobile, reproducible, and evolving, okay, then it must have capability at a molecular level to form large structures. And these structures should very quickly change their structures under very simple and normal stimuli. Like, for example, our hemoglobin or the molecules in our eye which detect light, the composition doesn't change, the structure changes whenever there is some interaction happening. So our proteins, all our proteins, they behave the way they behave because of their shape, not because of their composition. If you change their shape, the same protein will not function. Okay, so the structure of molecules, complex large molecules, and easy structural change is the key for life. And of course, you need reactions which are reversible reactions, which can happen in an environment which is very dynamic. For example, astronomers define a region called Goldilocks zone. Have you heard of that? It's Goldilocks zone is like if you find a star and it has many planets around it, Goldilocks zone is the part of the planetary system where water can exist in liquid form. Because the same water which gives us life, it is in vapor form, it won't support life. If it is in solid form, it won't support life, at least not easily. But liquid form will be a very dynamic environment to give meaning to life. Now, if I combine this large formation of molecular structure, quick and easy changes, the temperature should be between 20 or say 10 degrees to say 90 degrees or 80 degrees. If you put this, no other possibility exists. Only carbonaceous molecular life is possible. Of course, there are people who question the very definition of life. A computer program which self-replicates and evolves via AI can be declared as alive by some definition. So when I say life, if I say life based on macromolecular dynamic structure, which can undergo several reversible changes at very low energy stimuli, then only carbon life is possible. Okay. The next question, just to give you additional information, is the next question is, if it is carbon life, will it be similar to us? The similar has very serious connotations. For example, one of the long-standing problem in this field is to understand chirality. Our life is left-handed. Our DNA is left-handed. The amino acids we use are left-handed. For some strange reason, we are left-handed. You can produce right-handed DNA. You can produce right-handed other molecules, but life chooses left-handed. Certain molecules are chiral molecules. They have a handedness. Okay? So a DNA, for example, can have this kind of turns. One can be like this, one can be like this. For some strange reason, it is left-handed. So you can easily produce right-handed. So chemistry by itself doesn't stop you from producing both handedness, but somehow life has chosen left-handed. So then the question comes, is the choice of life being left-handed being choice because of the fundamental quantum mechanics of molecular structure? Or it is simply that this part of the world happened to choose left, there will be another part of the world where it will be right. So far, the evidences show that somehow nature selects left. Okay. And if we understand that, and if we can give the same level of certainty as what I told you about carbonaceous life, then you see the implication of that. That means if you ever find aliens, they may not look like us. They may not have 2 eyes and 2 ears. They may look physically very different. But deep down in their genotype and genome, they perhaps would be similar to us. That means a virus which affects us can affect them, and a virus which affects them can affect us. Okay? So these are open questions. The day we put full stop on this, we would understand the universe much better. And one of this handedness problem can be solved if you can build an instrument called a chiral mass spectrometer. It's an open challenge. You build a payload which can go to a place, take the molecule, not take a mass spectra only, identify the left-handedness. That'll be a great day for science. Like there are many such open issues we have yet to understand.
Questions? As much as I've studied or read about possibilities of life on different planets and moons of different planets, so I heard that there is possibility maybe earlier on there was water on Mars, so it is possible that there was life there. And I've also heard that Europa also has some water underneath, so it is possibility that there might be some kind of life on in the water. And again, as you said, in Titan, we see there are organic molecules. So there are different types of conditions in all these 3 places. So what do we look for? What are the signatures that we look for when we are trying to find that? Is there a possibility that there was life earlier on? Or what was your reason to particularly choose that Titan? Like, is it the availability of data that was the thing, or is it the question itself was very interesting for you?
I'll start with a statement which many scientists wouldn't like. Okay. Since I am a physicist, I will blame it onto physicists. Okay, but I can say that for any scientist. We don't look for the key where it is lost. We look for the key where there is light. Okay. So yes, partly what you said is true. Titan is interesting because we know about it. Okay. But yes, to a very large extent, Titan is a very good laboratory to mimic what could happen in an object which will have a sort of a gaseous distribution of these molecules. And it doesn't have to be a planet or a moon. Even the protoplanetary disk at some stage had similar conditions. So that is one reason why it is interesting. Second reason is, of course, data is available. We can see a lot of things and verify, which you cannot do for many other cases. About water, what comes to know now to humans is that water is quite common in liquid form in our solar system. For example, Cirrus was supposed to be a very dry, gray, black color planet with no dwarf planet. Cirrus is a dwarf planet sitting in asteroid belt, about 3.5 astronomical units between Mars and Jupiter. So people thought it's just a dry place, so not much attention was given. Then suddenly one day telescopes show that there is one white spot which has developed, suddenly appeared on Cirrus. So then they sent a spacecraft, a small spacecraft, to go and investigate there, not land, but take photographs. They discovered that that white spot was ice. The question was suddenly how ice can appear in a dry place. So then when they did little more investigation, it was found that just a few meters below the surface, the entire planet or mini planet is covered with liquid ocean water, which is mixed with water and salt in liquid form. So imagine how chemically active that environment would be. And then the top surface is 40% organic material. So you see, these kind of laboratories exist. Okay. The reason why I got into it, or the approach which we have taken, why that approach is interesting, is because, and I think this is a very nice place where we can discuss this aspect. When you look at the grandness of your surrounding, the ground, the geology, the atmosphere, sometimes it simply disorients you. Sometimes it rains, sometimes you see you see dark clouds, sometimes they rain, sometimes they don't rain. You don't know how to predict. It's predicting atmospheric behavior is one of the most challenging problems. So this behavior comes because there are many subsystems which are working together. That makes this problem very interesting, but very challenging. So when it comes to origin of life, it's the same problem. You have many things have to work correctly for the life to come. So now this we are trying to understand. So it has its own fun, but we know deeper inside our mind that we are not going to find the solution so soon. But sometimes it is more interesting to seek something rather than find it. This is one such journey.
Yeah.
I wanted to ask just one layman question. Actually, my son used to ask me. This question is from his side. But he asked that we are searching life on our own condition like water, oxygen. What if life exists without these conditions?
Yeah, so there are such possibilities. And people try to design such conditions. For example, one prediction is we can have silicon-based life deep inside the magma. Because if you have silicon-based life, then to have the same mechanical dynamism of life, the temperature has to be 800 degrees. Only then the silicon compounds can actually give you that kind of flexibility. The question then comes is, see, we generate our energy, or we sort of recycle our energy by using certain chemical reactions which are reversible, like ADP, ATP. This is what we burn sugar and so on, what would this silicon life would do? So then the possibility is it derives energy from the temperature instead of light. We derive our energy from light. It can derive energy from temperature. So like these ideas are there. Unfortunately, we do not know how to test them. But yes, there are possibilities. There are predictions or sort of propositions, I shouldn't say predictions, that there could be a plasma-like life forms on Sun itself. So then when it goes to that, then you start questioning what is life. You start defining the life, the meaning of life. Then it becomes a different question. Right? Because the kind of habits or kind of limitations those systems would have, if I put those limitations, perhaps a swarm of microscopic robots would also be life. So we are still to understand a lot.
But there is a possibility.
There is always a possibility.
So we have been successful in growing cells in labs. So as you said, there might be silicon-based life. So has anyone tried to produce that in a lab or any other possible life form which has anyone tried to produce that?
Not in my knowledge, because remember, even we are successful in growing artificially the cells in life. The starting point always is something which was naturally known to you. Okay. You can either take a natural DNA and then start expressing the proteins, or you sort of using a trick, you build your own DNA and then you express it. But all said and done, we have really not made cells
From scratch.
from scratch. We have either used a natural molecule and copied it, or natural template and then tried to match it and then make it. So there is still some time.
Any other question? So just one query I have. Garvit asked it partially. So let us say Indian exploring mission started with maybe Moon and then Mars. And in your presentation and your introduction also, I read that Venus now is the next target. So what is the motivation behind the next? Any special thing?
Yeah. So there's a actually the I'm very I'm very quite happy you asked this, because there is a certain uniqueness about Indian space program. Not many people actually appreciate certain things in India, because we normally have a very negative mindset about our own children, for whatever reasons. You can call it historical, colonial, whatever, but we tend to have that attitude. But there are certain facts which are very clear. If you look at Europe, okay, entire Europe, the population is almost close to Indian population, much more prosperous. There is no single country in Europe which has its own space program, self-supported space program. They have space agencies, but they don't have their own individual launching capability, design capability, building capability. They always work together as European Space Agency, and the launches are done by European Space Agency, not by France or UK or Germany. Okay, India, being so far away, so backward in technology, so poor in economy, is able to do it. It's not easy. Second, today in India, if you are associated with any university or academic institute in the country, you want to build a small instrument and fly, you get a free ride. No space agency offers that. You have to generate funds. If you go to NASA, you have to generate your funds. You have to pay them for the launch. You cannot get a free ride. In India today, Indian Space Agency offers this to Indian academics and researchers. So such opportunities you don't easily get. Now coming to the final point, and that is something really great about Indian space program. Because we are so isolated, because we are always under watch. Okay? When we successfully land on Moon, people read more news articles published by foreign news agencies saying why these people are doing this, rather than seeing that young engineers from ordinary engineering colleges, not IITs, ordinary engineering colleges are building these instruments world class and landing them in places where very few countries ever could go. In fact, the southern part of the southern pole, India was the first country. So Indian space program is always very, 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 very frugal. We really, really can see their struggle. They cannot fail. If they fail, there are 1,000 newspaper articles to support that. See, these people cannot do anything. So every failure is looked at as a validation that Indians are not good at doing technology. So this program has to walk on a knife edge. Therefore, they spend their money very carefully. I was involved in preparing and planning for this Venus mission. I know how much convincing we had to do to the government to let us fly to Venus. Okay, so every mission is planned very, very carefully. You have to really convince people who are not from the field to justify the amount of money we are spending. And though we spend much less than what the other agencies spend. So these missions are made with very, very detailed analysis. For example, there are 5 missions which are planned in next 6 to 8 years towards Venus. 5 missions. Out of that, 3 missions are very small, sort of flyby or small satellite missions. They don't have much very strong scientific goal. There are only 2 major missions which are having serious scientific goal, and they will actually go as orbiters. The one which is Indian, called Shukrayan, that is focusing on the upper atmosphere, atmospheric processes, and ionosphere of Venus. Whereas the other one, Da Vinci, it is more focused towards geology, surface, and below surface what is happening. So these are, this is why in next 10 years of time, I can say confidently, humanity will have any information about Venus atmosphere and ionosphere and exosphere will come only from Indian mission. There's no other possibility, because any mission anybody takes anywhere in the world, it takes 5 to 8 years to build and launch and do everything. So far, whatever has been officially planned, next 10 years, Indian space mission is the one which will give this data. So that is the main goal. For the moon mission, India is planning for a sample return. And that is an amazing thing. If we can get a sample back from moon, of course, we are not the first ones to do that, but imagine the kind of technological, expertise which it will give to us. Okay, so the next plan for moon is to land, collect a sample, seal it, and bring it back. That will be the thing. For Mars, next Mars mission, discussions are still going on, but as far as I know, nothing official has come out. Any possibilities are there. We may have a lander, may not have a lander, but again, there are many possibilities. I am not part of that discussion, so I don't know. But for Venus, it is entirely upper atmosphere, atmospheric processes, bit of surface, but mainly atmospheric processes. That is the goal. Yeah, thank you.
Small comment here.
It's
Yeah, regarding this ISRO's achievement, I would say that you're saying that we talked about our own agency, but I would say that we are really proud of ISRO. And then starting from Vikram Sarabhai, is the one, and then the great Naveen Narayanan, he is still alive. So they brought the cryogenic engine, they developed here from solid fuel to liquid fuel. So whatever they have given the vision, so ISRO is going on the same path. And we are really proud. Just, I think last month I met Professor Somnath, and then we had a huge discussion about ISRO journey. So, we are proud of ISRO, the way they are progressing, the best fund, and then there are many unsung heroes out there. So
Yes.
I think this negativity should go out
yes.
from the young generation, from the young mind. And ISRO is really doing very it. And then some of the previous scientists like Umesh Ramakant Kadhane, I salute him. He gave a great vision that time with Vikram Sarabhai and his leaders. Yeah. And
Yes.
one movie was there, I think,
Yeah.
Rocketry. If people have not watched, so please watch that movie, Rocketry.
Yeah, actually, that particular story was a bit tragic story, but it became very popular. But I can tell you, because I know some of these people, there were many people involved. Many people actually have suffered personal losses in the process of building this kind of organization. And even today, I can see when I work with my ISRO colleagues, the senior people, I know how much their personal life gets affected, the kind of effort they have to put. Because very simple logic, when I build an instrument in the lab, it is in the lab. If it doesn't work today, it will work tomorrow. If it doesn't work tomorrow, it will work day after tomorrow. You send a satellite on a rocket, it is halfway in the orbit. You cannot say that, oh, I forgot to put one bolt. If that, usko wapas bula lo, we will correct it and send it. You don't have such options. So they are always running on every possible limitation a technologist can have, and still they achieve their missions. It's a big effort, and it's a collective effort, and a lot of people were involved. Even in that case, even the cryogenic story, though he suffered very badly, personally he suffered because of some politics, we don't know what it was, but behind him there was a team, and that team managed to learn that expertise, bring to India, use it. And what is very important to understand and appreciate, yes, we learned a lot from the Western world. But a very, very important thing which we should not forget is we learned it by the fair way. Whenever we learned it openly, with all proper procedures done and credits given. For example, the Vikas engine, which is used in PSLV, was developed in collaboration with the French Space Agency. It was called Viking. And the main scientist from France who was actually supporting India was given Padma Shri. So, openly acknowledge, yes, we learned things from people, we adopted them, and that is the right way.
Yeah. Before I formally thank Professor Kadhane, I would just give you a context why he is here. So we have a very beautiful cosmic ray based cosmic ray neutrons based soil moisture sensing at IITM, and so we are collaborating to develop similar kind of system to measure soil moisture based on microstructured semiconductor neutron detector. So today we had some site deliberations and discussions. So we hope that with his expertise and with our in-house teams, with the climate observations group, we could be able to do something substantial in this regard. So thank you, Professor Kadhane, for visiting IITM, for visiting us, for giving a great talk and interacting. I think you gave a lot of glimpse into what has gone into different kind of planning and implementation. Thank you very much.
Thank you. Thank you.
Okay. Yeah, thank you.
It is surprising to know that they are here for CRA. And we were not involved in concepts. ऐसा नहीं चलता बोले ATM से सही उनको तुम्हारा